Hello, today's video is going to be on chemical equations and balancing chemical equations. So what we're going to start looking at are chemical reactions. Now, chemical reactions are the actual processes that we're going to see happening. So we're going to see where substances are going to be converted into new substances, and that's the key behind a chemical reaction. Now, if you remember back at the beginning of the year, we were talking about chemical changes. That's what a chemical reaction is. It's a chemical change that's going on to create a new substance. And the key here is that we're forming something new in these chemical reactions. So what we're going to do in the labs is you're going to see chemical reactions happening, and in order to talk about those chemical reactions, what we're going to need to do is convert them to chemical equations. Chemical equations are our way of describing what we see happening in the reactions without having to write down all the words. We're going to use our chemical formulas that we did in the last chapter, so that's going to come back into play, naming and writing compounds, and symbols to describe the chemical reactions. Well, here's your new symbols that you're going to want to know. The little plus sign means that something is going to react with, or really what it's doing is it's separating out our substances. Okay. Then we have the yield sign. Okay, we don't use a equal sign in chemistry. We use a yield sign, which means to produce or to form. Okay, so for example, a very common reaction we talk about is hydrogen. Okay, gas. So I'm going to put the state of matter that it is. So you might have hydrogen gas that you would see. Okay, so we would describe that with a chemical formula and a symbol to say what state of matter, and we're going to combine that with oxygen. And we're going to say that hydrogen plus oxygen is going to produce something or yield something. Okay, in this case, when we let these two react, what they're going to form is water. And that water would obviously be based on your observations in the lab. Maybe it's a liquid, maybe it's a gas, but whatever it is, you're going to indicate it with a chemical symbol, or I'm sorry, with the state of matter. So you've got solid, liquid, gas. Now for right now, we're only going to stick with the arrow pointing in one direction, and your arrow should always go towards the right. Okay, so I should not see any arrows going back in this direction. Okay, that is something you do not want to do in here. Okay, there will be later on in the second semester, we're going to actually come back and we're going to look at what are called reversible reactions, and that would be equilibrium. So the arrow can actually go backwards and forwards. Reactions can go in either direction. So for right now, we're staying with reactions that are going in one direction. They're non-reversible. So hydrogen, oxygen becomes water. All right, so you should be okay with these states of matter. It's just S, L, and G for the three states of matter. This one we're going to talk about more in the next section. We're going to talk about solutions, okay? And we're going to have solutions are when things are dissolved in water. What we use is the Latin word for water, which is aqueous or aqueous, and that's an AQ. So what that tells me is that I have something dissolved in water. So I might have something like sodium chloride aqueous. I'm going to talk more about what that means physically in another lesson, but for right now we have sodium. So what that means is you have table salt dissolved into water, and then it would react with whatever it is that it's going to react with. Okay. The other notations is that we sometimes put things above the arrows. These aren't too important, but if you add heat, like if in order for this reaction to happen, I might have to add heat to get this to happen. So I could either write the word heat, or sometimes we use a little triangle. Now catalysts, hopefully you know catalysts speed up chemical reactions. Okay, we'll talk more about catalysts as we move along. But the catalyst isn't really a reactant, and it's not a product. So what we're going to have to do with catalysts, if we have them, we just write the substance that is used as a catalyst above it. So platinum is a very common catalyst that speeds reactions up. Now the thing about the catalyst is that it's not used in the reaction, so we're not going to put it in the reactants or products. So it's just a vehicle or a device that's used to make the reactions go faster. Okay? Now, when you're writing chemical reactions from problems in the book or you haven't seen the experiment, I get this question all the time. What about the state of matter? How do I know if something's a solid, liquid, or gas? There's only a few times that I'm really going to be taking points off for this kind of thing because it comes down to really experience. The more we go along in the class and the year, you'll get better at doing this. So for right now, if in general, if it's an ionic compound, it's going to be a solid unless there's water present. And we'll talk about that later when we start talking about dissolving, because some ionic compounds will dissolve and others will not. And I'll show you how you can determine that for a later time. So I'll be really, relaxed on the grading of states of matter. I'm just more concerned that you're attempting to use them, they're not getting them accurate. Molecules tend to be liquids and gases, but again, they can be solids. Okay, but for the most part, molecules like water tends to be a liquid, carbon dioxide a gas, table salt's a solid. So ionic compounds, solids, molecules, liquids, and gases at room temperature. Acids, we're going to use a standard AQ for that. So anytime you have an acid, you're going to put the state of matter AQ because the acid will almost always, for you guys, be dissolved into water. Okay. For the elements, use the periodic table. I got that big giant one in the back of the room. If you use one in your book, it's pretty simple. Most of them are solids except for mercury and bromine, which are liquids. Everything else would be a gas on the right side, like the noble gases and chlorine and bromine and stuff. Okay, and then any solution that you have. So if it says a solution of this is reacted with something, solutions are always going to be AQ as well. Okay, so again, you might want to write this table down, pause this, and write these down so you have them in your notes. But that's pretty much a state of matter. And as I said, if I'm going to take points off of the incorrect state of matter, I will be very specific and tell you that I will do that. Okay? Alright, so let's take a look at our chemical equations. Alright, so let's say we have this, going back to this reaction for water. And I know a lot of you are probably already thinking, wait a minute, you have 2 oxygens over here, but only 1 over here. Where did the other oxygen go? Well, in order for this equation to be properly written, we have to balance the equations. Okay, so we're going to balance chemical equations. Okay, what we know about chemical reactions, if I start with hydrogen and oxygen, and I measure the mass on this side, and by the way, you should know that this side is your reactants, right? This half of the reaction, hydrogen and oxygen, are called reactants. Okay, and our reactants are always on the left side, and our products, what we're producing, is on the left side. Okay, so usually the arrow, no, almost always, the arrow is going to separate out your reactants from your products. So if we measure the mass of our reactants, it is going to be equal to the mass of our products. And this is a very fundamental property of chemistry. It's called the law of conservation of mass. That the mass before a reaction and the mass after a reaction is exactly the same. Now if we think about the individual atoms, well, the atoms each have masses, right? We know that hydrogen has a mass and oxygen has a mass, and on this side the mass of the hydrogen and oxygen are going to be the same. So what we really are saying when we say that the masses of the reactants are equal to the masses of the products, what we're saying is that the number of atoms on both sides of the reaction are the same. So instead of saying that the masses are the same on both sides, what we could say is that the number of atoms is actually the same. So number of atoms are what we're actually looking for. Because if you think about it, if I have 2 hydrogen here and 2 hydrogen here, wouldn't the mass be the same? Right? It would be exactly the same as it would be on both sides of the reaction. So really what we're doing when we're balancing equations, we are looking at number of atoms on the product side and the reactant side being exactly the same. Okay, now as you see, the masses can't be the same if I have 2 oxygens and only 1 over here. So what's going on here? Well, to understand this, we need to kind of look at what these physically mean. So if I take a look at this formula for oxygen, this is what oxygen looks like. It's 2 oxygen atoms bonded together, okay, with a double bond. We'll talk more about double bonds later. Okay, and if we look at hydrogen, what happens is we have hydrogen looks like this. Okay. So here's our hydrogens. Get rid of that. Hold on, I'll go away in a second. Hydrogen, oxygen. All right. So when we cause this reaction to happen, the first thing we have to do is we have to break the bonds. We have to split the bonds and break up these into individual atoms. Okay, so let's do that. Let's get rid of this hydrogen atom here and move it out of the way. Let's go ahead and get this hydrogen atom out of the way. Now we got the hydrogens all split, the oxygens are all split, and we can now see that we've got the individual atoms. Now what we're going to do is we're going to reconstruct this into water molecules. So to do that, if I'm going to make a water molecule, I need an oxygen and I need 2 hydrogens. And that would make my water molecule. So let's just draw in the bond here. So we're creating new bonds when we are reacting these together. And there's our water molecule. Okay? Alright, now, problem is, if I look over here, I'm missing, and I have an extra oxygen that's just kind of floating around on the product side. Now that can't happen, so at minimum, what I need to have is I need to have another, whoops, undo that, that's what I want. I need to have another hydrogen atom. Okay, so I need another molecule of hydrogen in order for this to react. So I had to get 2 of these hydrogens. So therefore, what I would do is I'd put a coefficient of 2 in here. Because at minimum, I needed to have 2 of these, the hydrogens and 1 of the oxygens in order for this reaction to happen. Okay? So therefore, I can now bring this over here, and now I can form the remainder of my material, okay, which would be my water. Now, as a result of doing this, how many water molecules do I actually have when I'm finished? I actually have 2 water molecules. Okay, so there is a complete balanced equation. So what this is telling me over here, by the way, what this is saying is that if I were to have 2 hydrogens, so I have 2 atoms of hydrogen, okay, or 2 molecules of hydrogen, 4 atoms altogether, and oxygen, I had 2 of them, and over here I get 2 waters to be formed. So the number in the front is called a coefficient. And what the coefficient tells you is how many molecules of your substance you have. So this 2 means I have 2 of these. You can imagine there's a 1 here, and it means you have 1 oxygen and 2 water molecules. And each water molecule has 2 hydrogen atoms. So therefore, on this side I have 4 hydrogens, and I have oxygens equal to 2. On this side I have 4 hydrogens, okay, and on this side I also have 2 oxygens. So what we're going to do is we're going to use coefficients to balance the equations. Okay, so coefficients go in the front to balance our equations. Okay, so we cannot change the subscripts. And don't forget that hydrogen has to exist as a diatomic, oxygen exists as a diatomic, and we have the correct formula for water. Because if you think about it, the easiest way that I could balance this equation, wouldn't it have been so much easier to put this here? Wouldn't that have made 2 oxygens, 2 hydrogens, 2 oxygens, 2 hydrogens? The problem with putting that there is that's not the formula for water. We know that water is H2O, not H2O2. So we cannot change our formulas. So once the formulas are written, we then use coefficients to balance. So that's why it's really important to make sure that you know how to write your formulas properly. Because if you don't write the formulas properly, then you can have a lot of trouble with the balancing. Okay, I'm going to end this video right now. If you want to watch the second video, I'm going to do some other practice problems on balancing, and I'll go through the steps of balancing in the second video. Alright, so that's just the basics, and I'll talk to you guys later.